Calculate the electric field at one corner of a square 1 meter on a side if the other three corners are occupied by 2.25 times 10 power minus 6 coulomb charges. So our task is to calculate the electric field at one corner. So for that I need a square. Suppose you draw a square at here. So this is a square of side 1 meter. Let me call distance equal to 1 meter. If I take them as three corners occupied by 2.25 times 10 power minus 6 coulomb. So that I'm calling Q1. That's I'm calling Q1, Q2. No need to call Q1, Q2. Just you take all are having same quantity. It's a Q and also Q and also Q. And Q equal to 2.25 times 10 power minus 6 coulomb. And distance d equal to 1.00 meter. And I need to calculate the electric field at fourth corner at here. For that, if it is charge q1, if this is the charge at this point, the electric field direction is along in this direction. At this corner, that is the electric field due to this charge. And due to this charge, the electric field at the same point is along in this direction. Due to this charge, the electric field is along in this direction. Okay. Now, if I can call electric field due to three charges, first, second and third. So this is the electric field due to E1, this is E2 and this is E3. Okay. Now first you write electric field due to first E1 equal to K times Q1 by the distance here, the distance equal to D, and this is also D, this is also D as a square. It's better to mention to me Q1 equal to Q2 equal to Q3. All are having same magnitude. So I can take that as, for a moment, D square. AQ by D square. D is the distance. Now I want to know that since electric field is a vector, so this is along the x-axis. So the component along the x-axis equal to E1x equal to KQ1 by D square. Since this is coming along the x-axis, if you can draw the x-axis at here so that you can understand better carefully. So this is the x-axis, positive x, and this is the negative x and the positive y and the negative y. So E1 is along the positive x-axis, its component. But there is no component of the E1 in the y-axis. So that component goes to 0. Why I am writing the components? So you will understand. Just wait a second. An electric field due to second charge Q2, E2 equal to K times and the q2 times and the distance. Now here the distance from q2 to at here. Now q2 to at there. Now if you see from this right triangle, so this is hypotenuse. You can apply the Pythagorean theorem at there, so you will get, so hypotenuse square is equal to d square plus d square. So hypotenuse square is equal to 2d square. So hypotenuse equal to square root of 2d square. So here my hypotenuse equal to r, but r square equal to 2d square. So its value goes to 2d square. So I can write that value at here. It is a 2d square. Now here this is the electric field due to second charge. So let me make a correction. This is the second charge, this is the third charge, this is the ones. And now the E2 is in this xy plane. Now the E2 is having components. We already learned that in the vectors. E2 is making an angle theta. So that's why this E2 is resolved into the two components. One is the horizontal component, second one is the vertical component. The horizontal component is along the x-axis, that I can write E2x equal to k q2 by r square 2d square, the angle between them. So the same angle, since it's square, its angle goes to 45 degrees. So there also angle goes to 45 degrees. 2d square cos 45 degree. So if you can simplify that further, so E2x equal to kq2 by 2d square cos 45 1 over root 2. And I wish I could do further simplification. E2x equal to, I can write k times root 2q by 4d square. That is the x component. And what about the y component? The y component at here is E2y equal to, now if you can see, the y component is the component of the E2 is resolving to the along the horizontal axis and the vertical axis. Here the vertical axis is a y, that you can take as in terms of the sine. So k q2 by 2d square sine 45. Sin 45 value is equal to cos 45. So there is no change of the value. kq2 by 2d square 1 over root 2. So E2y equal to k root 2q by 4d square. So this is the electric field due to the y component. Now the electric field due to the third charge, and E3, the electric field third charge equal to k q3 by, now where is the electric field? So that is the q3 is along the straight, it means it do not have any x component. So you can write that kq3 by d square. So this is only resolved into the two components, I can write E3x component goes to 0. I wish I can put comma at here, but this is only the component of the E3 along the y component goes to kq3 by d square. Now we need to write the total electric field. Total electric field along the x components equal to E1x plus E2x plus E3x. Ex equal to E1x equal to kq by d square plus k root 2q by 4d square plus the third component goes to 0. Similarly, total along the y component goes to E1y plus E2y plus E3y. And E3y. Therefore, Ey you can write as, along the first charge there is no y component, but for the second charge it is y component is there, k root 2q by 4d square. For the third charge the y component is there, kq by d square. Now if we apply the parallelogram law at there, by applying the parallelogram law, we can combine these two components by applying the parallelogram law at here to get the resultant electric field. We need to combine all the x components and we need to combine all the y components. So you can write that electric field of the x component. Here I can take it out of the common factor, kq by d square of 1 plus root 2 by 4, and here also you can take it out of the common, Ey equal to kq by d square root 2 by 4 plus 1. And now the electric field net, final electric field, if you can apply the parallelogram law vector, E equal to square root of Ex square plus Ey square. That is the resultant electric field formula. If you can substitute these two Ex and Ey values at here, so kq by d square of 1 plus root 2 by 4 whole square plus kq by d square of root 2 by 4 plus 1 whole square. So these two are the similar terms and square is there. You can add and take it out the common. So I can pull kq by d square out of the root along with 1 plus root 2 by 4 out of the root, and the leftover term is root 2. And if we can simplify that, we can get the final result as kq by d square root 2 plus 1 by 2. If you can do this simple algebra, you can get it. Now substitute the end values to get the end result. The electric field net, put the all these parameter values. It's the k value 9 times 10 power 9 Newton meter square per coulomb square, and charge q is given 2.0 25 times 10 power minus 6 coulomb by distance 1 meter 1.00 meters square, and rest of the terms root 2 plus 1 by 2. Simplify the net. By simplifying this above expression, you will end up with the result 8.37 times 10 power 4 Newton per Coulomb. So this is the magnitude of the electric field. For the direction we can use the vectors direction theta equal to tan inverse electric field Ey by electric field Ex. By seeing that, there you can understand from the figure that theta goes to 45 degrees from the x direction. So the resultant electric field net equal to 3.87 times the resultant of these three electric field at this corner, 3.87 times 10 power 4 Newton per Coulomb, and the direction equal to 45 degree.